Greetings of the day to all of you. Our today's lecture is continuation of last lecture. In our last lecture, we discussed, over-modulation from the point of view of conventional space vector PWM. We first discussed over-modulation for m greater than 1.15 but less than 1.33. That is, we had taken m equal to 1.2, and then we discussed for m equal to 1.33. And we found that if for over-modulation, if modulation index is greater than 1.15 and up to 1.33, we are in over-modulation zone 1. And if modulation index is greater than 1.33, we are in over-modulation zone 2. So today we are going to discuss over-modulation zone 2. So we are going to discuss over-modulation with m equal to 2, which is over-modulation zone 2. I will write here OverModulation Zone 2. Let us quickly draw various waveforms. First of all, I will draw three-phase modulating waves, modified modulating waves. Modulating waves or modulating signals. So first of all, we have, these are the modified modulating waves. This is one. And this is over-modulation. Here m is equal to 2. This is mr star. And then my star will be like this. This is my star. And mb star will be like this. MB star. So you can see, over-modulation is there for, this is one, over-modulation is there. See, for example, pulse dropping is for a larger period. And if you see this period, yahan se yahan tak, it is greater than 150 degrees. Because MR star is greater than triangular carrier wave peak for a larger period, and during this period, there will be bus clamping or there will be pulse dropping. So pulse dropping is greater than 150 degrees. This is similar to m equal to 3 for, sine triangle PWM. Similar to modulation index equal to 3 for sine triangle PWM. Sine triangle PWM. So m equal to 2 for conventional space vector based PWM will give same results as m equal to 3 for sine triangle PWM as far as over-modulation is considered. Let us quickly draw three-phase average pole voltages. Three-phase average pole voltages. Pole voltages will be like this. Our pole voltages will be, for example, this is our pole voltage, average pole voltage, VRO average. It's 0.5, and this is minus 0.5. Right? And this is Vy. This is VYO average, and VBO average will be somewhere here. This is VBO average. So these are three average pole voltages. You can see that pulse dropping is for greater than 150 degrees, right? What about three-phase average line voltages? Now our line voltage, because overmodulation is high now, M is equal to 2, our line voltages will, they are moving slowly towards the quasi-square wave, or our phase to neutral voltages are slowly moving. They are very near to 6-step voltages. Let us try to see the nature of three-phase average line voltages. Three-phase average line voltages. So line voltage will be at 1.0 for fairly longer period. And then it will be 0 for some time, and then -1 for fairly longer period. So this is line voltage, average line voltage, VR by average. What about average line voltage, V by B average? V by B average will be like this. This is line voltage V by B average. Similarly, you can draw VBR average. Sorry. This is average line voltage VBR average. So these are three-phase line voltages. VR by average, V by B average, VBR average. You can see the line voltages are having maximum value 1 for a fairly longer period. So therefore, if you find their RMS value, a fundamental component of these line voltages, the RMS value of fundamental component of these line voltages will be fairly high. Okay, so that means inverter output voltage will further increase because of more overmodulation, because of M equal to 2. What about three-phase average phase voltages? I will now write three-phase average line to neutral voltages, or phase voltages. Okay, so there will be very nearly 3-step, not exactly 3-step, but very nearly 3-step voltages like this. Excuse me. Okay, this is 0.6 here. So it is more than 0.6. Its peak is positive and negative peaks are more than 0.6. This is 0.6 minus 0.6. So this is phase voltage or line to neutral voltage, VRN average. Okay. What about VYN average? VYN average will be like this. It will start from here. It will be having same. I will show it dotted because it will overlap with this. And it will be like this. Similarly here it will overlap. This is VYN average, and VBN average will be like this. this is VB and average. So these are three line to neutral voltages. Okay. Now if you compare phase voltage and line to neutral voltage for one phase, say phase R, it will be like this. The comparison will be like this. For example, this is our average pole voltage, VRO average 0.5 and minus 0.5, and our this is phase R average pole voltage, VRO average, and phase R average phase voltage or line to neutral voltage will be like this. So this is VRN average and ये आपका 0.6 है. So it is slightly greater than 0.6 and minus 0.6. So this is the comparison between pole voltage and phase voltage. You can see phase voltage is different from average. Average phase voltage VRN average is different from average pole voltage VRO average, because this is the effect of over-modulation. Okay. Now you can show variation of magnitude of the rotating reference vector over a line cycle. Magnitude of average rotating reference voltage vector. Rotating reference voltage vector, that is Vref over a line cycle. So it will be like this. This is omega t. It will go like this. This is 360 degrees, full line cycle, 0 to 360 degrees. This value is 1.0 and this line is 0.8. So it is greater than 0.8 and it is 1.0. And if you see magnitude of average rotating reference vector over one sector, so if you see Vref over one sector, it will look like this. For example, this is omega t, say 90 degrees to 150 degrees. And this is, here also you can write, this is Vref magnitude, and here also you can write Vref magnitude. So it varies like this. This is 1.0 and ये line है आपकी 0.8 and ये आपका 90 to 150 degree in one sector. You can see in one sector it is like this. Start from here, इससे एक sector complete हो जाता है. Okay, so it is not constant. It's constant for some time and then like this. It is similar to m equal to 3 for sine triangle PWM. In sine triangle PWM, we got similar, variation of rotating reference vector over one sector and over one line cycle. And here you can see active vector 1 will be applied. It will be applied for a longer period of time. That's why its magnitude is constant. And then here, during this period, there will be switching between active vector 1 and active vector 2. I will write here switching between active vector 1 and active vector 2, and during this period only active vector 2 will be applied. So first active vector 1 will be applied for some time. Okay, so this will be applied, this will not be applied for a very small period, it will be applied over a large number of samples for some time, and then there will be switching between active vector 1 and active vector 2, no null vector is applied, and then active vector 2 will again be applied for some fairly good time. Okay, what about variation of angle of rotating reference vector over a sector? Variation of angle of rotating reference vector, angle of rotating reference vector over S sector. So it is something like this. This is omega t, say 90 degrees to 150 degrees. And it's something like this. It's alpha, angle of rotating reference vector 0. And then it increases linearly and then it remains constant. This is 90 degrees to 150 degrees. Okay. During this period, your angle of rotating reference vector does not change. That means rotating, because during this period, active vector 1 is applied and your reference vector 1 is applied and angle does not change. I mean, only active vector 1 is applied for maybe 10 degrees or 5 degrees or 10 degrees. And then there is switching between 1 and 2. Both active vectors are applied, no null vector will be applied, and your rotating reference vector will move along the hexagon. And then here active vector 2 only is applied. So when it reaches active vector 2, only active vector 2 is applied and it remains there for some time. Okay. So therefore the nature of average voltage vector applied will be something like this, and it is something like this. Average voltage vector applied. Average voltage vector applied across the load. This is active vector 1, 2, 3, 4, 5, 6. Null vector 0 and null vector 7. Active vector 1 is applied for fairly long time period, and then it remains here for some time, and then there is switching between active vector 2 and active vector 1 and active vector 2. During this period 1 and 2 switching, no null vector is applied. So that means your reference vector moves along the hexagon till it reaches and it remains here for some time. Remains here for fairly longer time or for some time. So 1 is applied for some time, 2 is also applied for some time, and 1 and 2 switching occurs. Okay. So you start like this in sector 1. Active vector 1 is applied, no switching takes place. It's applied for some time. And then switching between active vector 1 and active vector 2 applies in each sample, and your rotating reference vector traces the hexagonal trajectory, no circular trajectory. And then it remains, it applies active vector 2 for fairly longer time. Okay, this is in sector 1, and in sector 2, active vector 2 is applied for some time, no switching occurs, and then there is switching between active vector 2 and active vector 3, no null vector is applied, and your rotating reference vector moves along the hexagonal trajectory like this, and then active vector 3 is applied again for some fairly longer time, and this repeats in all the sectors. So this is how, this is the similar thing, the same results you obtained when you applied in sine triangle PWM for m equal to 3. So m equal to 2 for conventional space vector PWM technique is similar to m equal to 3 for sine triangle PWM technique. Okay, and let us summarize what we have seen, for what we have observed for m greater than 1.3. Summary for over-modulation with m greater than 1.33. For example, we have taken here m equal to 2, which is greater than 1.33. First point that we have observed is that at any instant of time, two modulating signals exceed the carrier peak in any carrier cycle, in any given carrier cycle. Okay, this is first observation. Second observation is that only one phase switches. That means two phases have pulse dropping and only one phase switches between the active states. No null vector is applied. Only active vectors or active states are applied. Okay. Then third point is that pulse dropping for more than 120 degrees duration occurs in each half cycle. In each half cycle for each phase. Just recall, few minutes back I have shown you in the waveform that pulse dropping occurs for more than 150 degrees. That was for m equal to 2. So m greater than 1.33, that is 1.33 to 2, your pulse dropping will be always greater than 120 degrees. And it may be as high as 150 degrees or even more than 150 degrees. For example, for m equal to 2, we have observed that pulse dropping for more than 150 degree occurs. So in general, for m greater than 1.33, for m equal to 1.33, we have previously seen that pulse dropping for 120 degrees occurs. But for m greater than 1.33, pulse dropping for more than 120 degree occurs. Okay, then very high low frequency distortion, low frequency harmonic distortion occurs in inverter output voltages. So level of distortion in inverter output voltages is high as far as low frequency harmonic distortion is concerned. Then another point is that average voltage vector varies in a average voltage vector varies over a line cycle. It's not constant, it varies. Okay. Then what about angle of rotating reference vector? Angle of average reference vector varies in a piecewise linear manner. Piecewise linear fashion with time, or with fundamental angle with time. You have seen it varies like this, piecewise linear manner. And finally, what about trajectory? Trajectory of tip of rotating reference vector. Tip of reference vector is fully hexagonal, not circular at all, is fully hexagonal. Okay, so these are some of the observations we have made while discussing overmodulation in conventional space vector PWM based inverter for m greater than 1.33. Okay, and if you want to degenerate your inverter into 6-step or square wave mode of operation, then take m greater than 2. If you take m greater than 2, your inverter will degenerate into square wave mode of operation, and 3-phase pole voltages, 3-phase average pole voltages will be like this. 3-phase average pole voltages will be like this. I can draw them separately. For example, this is average pole voltage, VRO average. It will be like this. It's 180 degrees. There is pulse dropping for entire half cycle, 180 degrees. Okay. What about VYO average? VYO average, that starts after 120 degrees, say somewhere here. It's like this. And what about VBO average? Average pole voltage VBO average. That will start after another 120 degrees like this, like this. Okay. So these are three-phase average pole voltages. What about three-phase average line voltages? They will be quasi-square wave in nature. I will write here three-phase average line voltages. Three-phase average line voltages. So they will be like this. I can draw them separately. This is average line voltage, VR by average. It is like this. For example, so it is like this. So average line voltage V by B average is like, it will start after 120 degrees. यहाँ से so it is something like this. Similarly, ऐसे. And what about average line voltage VBR average? It will start after another 120 degrees like this. Okay, so these are our three-phase average line voltages. They are Cauchy square wave. Okay, what about three-phase average phase to line to neutral or phase voltages? Three-phase average phase voltages or line to neutral voltages. So they will be something like this. I can show them. This is average line to neutral voltage or average phase voltage VRN average. It will be like this. 1/3 VDC, 6-step operation. This is 2/3 VDC. Then again 1/3 VDC, then minus 1/3 VDC. Then minus 2/3 VDC. Okay, right? So this is phase voltage VRN average. What about VYN average? It will also be 6-step in nature. It will start from here. यहाँ से शुरू होगा. So this is VYN average, and similarly you can write VBN average. Average phase voltage VBN average. It will also start after 120 degrees. यहाँ से शुरू होगा. Sorry. Excuse me. यहाँ से. So this is average phase voltage VBN. Okay, so this is Cauchy square wave in nature. And if you compare pole voltage for phase R with its corresponding phase voltage, this is average pole voltage VRO average, and corresponding phase voltage will be like this. This is corresponding phase voltage VRN average. You can see average phase voltage is totally different from average pole voltage. And what type of voltage vector will be applied? Will there be any switching? There will be no switching at all. So average voltage vector applied. Average voltage vector applied across the load. active vector 1, active vector 2, active vector 3, active vector 4, active vector 5 with switching sequence minus minus plus, and active vector 6 plus minus plus, null vector 0 with switching sequence minus minus minus, and null vector 7 plus plus plus. This is our hexagon. Our reference vector will not be rotating at all. Reference vector will get applied here. So it will apply active vector 1 for 60-degree duration. After 60 degrees, it will not move, it will not rotate. It will neither rotate in circular trajectory, not along hexagon. It will jump. I mean, active vector 1 will go and then active vector 2 will be applied. Active vector 2 will also be applied for 60-degree duration. After 60-degree duration, the active vector 3 will be applied for 60-degree duration. Then active vector 4 will be applied for 60-degree duration. Then active vector 5 will be applied for 60-degree duration. And active vector 6 will be applied for 60-degree duration. So there is no rotating reference vector. We don't have any rotating. Our reference vector is same as these active vectors. Active vector 1 applied for 60-degree duration. Then active vector 2 will be applied for another 60-degree duration. Then 3, 4, 5, 6, that's it. And it will give 3-phase Cauchy square wave voltage, line voltage like this. And 3-phase 6-step phase voltage like this. Line voltages will be Cauchy square wave in nature and phase voltages will be 6-step. So this is square wave or 6-step mode of operation. Okay. Right. So I would advise you to go through certain references. I will at the end of the lecture give you some references. So that's all about over-modulation in PWM voltage source inverters from conventional space vector PWM perspective. Okay, if you are not using sine triangle PWM as your modulation algorithm, you are using conventional space vector PWM as your modulation algorithm. We have discussed various ranges of modulation in DCs, which will result in over-modulation of inverter. Okay, and we have found that m equal to 1.33 gives same results as m equal to 2. M equal to 1.33 gives same results in space vector based PWM based inverter as m equal to 2 for sine triangle PWM, and m equal to 2 for conventional space vector PWM technique gives same over modulation results as m equal to 3 for sine triangle PWM. Okay, we have also found that for m greater than 1.15 but less than 1.13, that's over modulation zone 1. Our rotating reference vector will trace partly circular and partly hexagonal trajectory. For m equal to 1.33, it will trace only hexagonal trajectory. Okay, and for m greater than 1.33, we will have OverModulation Zone II. It will trace hexagonal trajectory, but it will stay at a particular vector, say active vector 1 for some time, more time, and it will remain at active vector 2 for some more time, and then in between active vector 1 and active vector 2, there will be switching between active vectors 1 and 2. And for 6-step operation, your m has to be greater than 2. So m equal to 2 for conventional space vector based PWM technique is similar to m equal to 3 for sine triangle PWM technique as far as over-modulation is concerned. Now, there is some literature. If you find in the literature, over-modulation in space vector modulated inverters, they have developed some standard over-modulation algorithm. So I will write here standard over-modulation algorithm. Standard over-modulation algorithm in conventional space vector or space vector modulated inverters, voltage source inverters. So it is something like this. First of all, we have over-modulation zone 1. Over-modulation zone 1. This is if M is greater than 1.15 up to M equal to 1.33. This is over-modulation zone 1. So our, if you draw the space vector diagram again, this is active vector 1 again, vector 2, 3, 4, 5, and 6, and these are null vectors 0 and 7. This is your hexagon. Okay. If you see the circular trajectory may be something like this. Okay. For example, यहाँ से यहाँ अगर आप देखें, this is circular. यहाँ से यहाँ तक ये circular है. From here to here, this alpha, your rotating reference vector will be tracing circular trajectory. This angle is called alpha circular, alpha CIR. And what will be the magnitude of circular voltage? This is called, this reference vector is called V circular. Okay. And it has been found that V CIR, that is magnitude of reference vector V circle, which is in this V circle, can be varied from 0.866 to 1, and alpha circular can be varied from 30 degrees to 0 degree. For example, अगर आपका alpha circular 30 degree है, your V circular magnitude of rotating reference vector is 0.866, and as you move from 0 to 30 or 30 degrees to 0, V circular amplitude will change from 0.866 to 1. Okay. So therefore applied voltage vector will be, so therefore I will write here applied average voltage vectors, applied voltage vector will be Vp. In general, we call it Vp. It is given by this formula, 0.866 VDC by cosine of 30 degrees minus alpha p, if alpha circular is less than alpha ref, less than 60 degrees minus alpha circular. If your angle of rotating reference vector is greater than alpha circular, which we have defined just few moments back, but less than 60 degrees minus alpha circular, then your applied voltage vector is given by this formula. Now you may ask a question, what is the origin of this formula, where from we got it? I am not going to derive it. I am going to give you references, some research publications, especially IEEE transaction publications, and reference of a book where from you can get this formula, the derivation of this formula. Okay. And Vp, applied voltage vector, is exactly equal to V circular. Okay. Otherwise. Okay. So here I can write Vp is equal to 0.866 VDC by cos of 30 degrees minus alpha p, when reference voltage vector Vref is in hexagonal part of trajectory. We have seen that in over-modulation zone 1, just about half an hour or 45 minutes back, we have discussed if our modulation index is greater than 1.15 but less than 1.33, we are in In fact, up to 1.33 we are in overmodulation zone 1, and in overmodulation zone 1 we have seen that the trajectory of rotating reference tip of the rotating reference vector is partly circular and partly hexagonal. And if trajectory of rotating reference vector is hexagonal part of trajectory, then applied voltage vector is given by this formula, remember it. And if your rotating reference vector is moving along circular trajectory, then it is given by this formula. Okay, यहाँ पे मैं लिखूंगा when Vref is in circular region of trajectory. So therefore, if your Vref is moving along the circle, then applied voltage vector is given by this formula. And if rotating reference vector is moving along the hexagonal part of the trajectory, then it is given by this formula. Remember this. And what about dual times? How do we find dual time? Now this Vp is nothing but it is Vref. In conventional space vector PWM, I mean when we are not discussing overmodulation, then it is written as Vref. So Vref is given by rotating reference vector is given by either by this formula if your rotating reference vector is moving along hexagonal trajectory, or reference rotating vector is given by this Vsir if it is moving in the circular trajectory of if its trajectory is circular. Okay, so how to find the dwell times? So dwell times are found by this formula, Vp in Ts using volt second balance, We can calculate dwell times like this. Vp/Ts is equal to V1T1 plus V2T2 plus VZ/Tz. I mean, active vector 1 is applied for time interval T1 as we do in conventional space vector PWM technique. Active vector 2 is applied for time interval T2, and null vector is Vz is applied for time interval Tz. So this volt second plus this volt second plus this volt second should be equal to reference volt second. Vp is basically reference voltage vector, Vp into Ts, right? Where Ts is equal to T1 plus T2 plus Tz, which means the null vector time is equal to subcycle interval minus T1 plus minus times T1 plus T2. And what is this T1 given by? T1 is given by Vp sine of 60 degrees minus alpha p by Vdc sine 60 degrees into Ts. Time interval T2 is given by, dwell time T2 is given by Vp sine alpha p by Vdc sine 60 degrees into Ts, and Tz is given by Ts minus T1 minus T2. This is the same formula which we have discussed in conventional space vector PWM, with the only difference there we were writing Vref, here we are writing Vp. Because if Vp, why we are writing Vp? Because Vp is different for different trajectories. There we were considering only under modulation, linear modulation. But in overmodulation, Vp is different. If it is traveling, if the trajectory of rotating reference vector is circular, then Vp is given by this formula, Vsir, circular. And if it is trajectory is hexagonal, then Vp is given by different formula which I had written just few moments back, that is 0.866 Vdc by cos of 30 degrees minus alpha p. Okay, so it depends upon what is the trajectory of your rotating reference vector, and this is how dwell times are calculated. So this is for overmodulation zone 1. What about overmodulation? What about the algorithm for overmodulation? This is how we calculate dwell times, we calculate rotating reference vector in overmodulation mode 1. This is a generalized algorithm, standard algorithm. You can find it from research papers. And what about overmodulation zone 2? Overmodulation zone 2. Overmodulation zone means when m is greater than 1.33. Okay, that gives overmodulation zone 2. And in overmodulation zone 2, something like this. 1, 2, 3. These are active vectors and these are null vectors. as far as these vectors around V1 are concerned, they are merged into V1. Okay, so I will write here for this, यहाँ से यहाँ तक, for this period or for this angle, all vectors are merged, M-E-R-G-D, merged into V1. So that means effectively only V1 is applied. और इसी तरह इसके आसपास जो ये वेक्टर है V2 यहाँ अप्लाई करते हैं, only active vector V2 is applied, and then in between active vector 1 and active vector 2 is applied. And for m greater than 1.33, active vector 1 V1 will be applied for fairly long time. So आपका एंगल ऐसे होगा, ये कांस्टेंट रहेगा, and then V1 and V2 will be applied, and angle will vary linearly, and then for fairly long time 2 will be applied, and angle आपका फिर से कांस्टेंट रहेगा. Okay, this is for m greater than 1.33. And then how do you calculate these angles? I can note down here. I can give you the references from which you will get these formulae. Alpha p is equal to 0 degree if 0 is less than alpha ref less than alpha h, which is called holding angle. Say for example 10 degrees. 10 degrees, अगर आपका alpha 10 degrees है, 0 to alpha h 10 degrees, then alpha p is 0. And it is given by this formula, pi by 6 into alpha ref minus alpha h by pi by 6 minus alpha h. By the way, what is this alpha h? मैंने आपको कहा कि active vector 1 is applied for fairly long time, and that angle for which this active vector 1 is applied, that's called holding angle, alpha h. So here you can write, if alpha h is less than alpha ref less than 60 degrees minus alpha h. This is the algorithm, general algorithm, which has been given by researchers through the research publications, which is in the form of some books also. So you can go through this. I am not giving you the details, the formulae. You can just remember. And when you apply the OverModulation Zone II through simulations, for example, in your space vector modulated voltage source inverter, you can use these formula for calculation of these angles. And it is equal to pi by 3 if this is the case, 60 degrees minus alpha h is less than alpha ref less than 60 degrees. And applied reference voltage vector is given by this formula, 0.866 VDC by cos of 30 degrees minus alpha p. Alpha p कहाँ से आपको मिलेगा? यहाँ से. Alpha p will be either 0, if this is the condition, it will be pi by 6 into alpha ref minus alpha h by pi by 6 minus alpha h. If this is the condition, अगर alpha ref इस range में है और अगर आपका alpha ref इस range में है, then it is pi by 3. So accordingly, once you apply this algorithm and you know what is the range, whether your rotating reference vector is within this range or within this range or within this range, accordingly you may either apply alpha p here equal to 0 or by this formula or by pi by 3, and you can find rotating reference vector. यह आपका Vp जो है, it's rotating reference vector. And I have already told you that in OverModulation Zone II, only active vector, 2 active vectors, 1 and 2 are applied, and there is no null vector is applied. No null vector is applied. Okay. So therefore, using volt-second balance, how can you calculate dwell times? Using volt-second balance, Vp into Ts is equal to V1 T1 plus V2 T2. I am not writing plus Vz Tz because we are not using null vector at all. We are using only active vectors, V1 and 2. Okay, we are not using any null vector. Then this Ts subcycle time is given by T1 plus T2, and then this dwell time T1 is given by Vp sine of 60 degrees minus alpha p by VDC into sine of 60 degrees into TS, and dwell time T2 for active vector V2 is given by VP into sine alpha P by VDC into sine of 60 degrees into TS. That's it. Alpha P you can calculate. Just few moments back I have given you the formula for calculating alpha P. I have given you the formula for calculating VP also. Substitute in this, find dual times, according to those dual times from the lookup table, get the switching sequence, apply gating pulses to inverter switches, and your inverter will run in the over-modulation mode zone 2 automatically, okay, using conventional space vector PWM. Okay, so that's all. So this is the generalized modulation algorithm, which is generally developed by researchers and which is given, which can be used for running your inverter using conventional space vector PWM technique in over-modulation mode. And I am going to give you some very important references. Please go through these references. So let me give you some references. Some very important references. This is one of the references which you can go through. I'm just displaying it for you. Over-modulation these references are analysis of over-modulation in sine triangle PWM. First reference is by S. Venugopal, and the title of the research paper is you can see here, study on over-modulation methods for PWM inverter fed AC drives, MSc Engineering thesis from Indian Institute of Science, Bangalore, May 2006. Another is M.K. Modi, S. Venugopal, and G. Narayanan, analysis of over-modulation in sine triangle PWM from a space vector perspective. It is, you can find in one conference paper, National Power Electronics Conference, NPEC. It was held in 2010 at IIT Roorkee. Another is M.K. Modi, S. Venugopal, and G. Narayanan. The title of the research paper is Space Vector-Based Analysis of Over-Modulation in Triangle Comparison-Based PWM for Voltage Source Inverter. Sadhana is there is some journal of the name of Sadhana. I have not gone through this journal. You can search it on the Google, and you can, if possible, you can download this research paper and study this research paper. There's some for space vector over-modulation in conventional space vector PWM had inverter. There are some references. Yeah, there are some references. For example, analysis of over-modulation in common mode injection PWM means conventional space vector PWM. S. Venugopal, study on over-modulation method for PWM inverter fed drives. The same thesis. This is space vector based analysis of over-modulation in triangle comparison based PWM for voltage source inverter. And there are some more references, a couple or 2 to 3 references. Yes. Yeah, references over-modulation algorithms for low switching frequency space vector based PWM. G. Narayanan and V.T. Ranganathan, an over-modulation algorithm for space vector modulated inverters and its application to low switching frequency PWM techniques. IEEE proceedings. Then another is by G. Narayanan and V.T. Ranganathan, 2 novel synchronized bus clamping PWM techniques based on space vector approach for high power drives. IEEE transactions on power electronics. Another is G. Narayanan and V.T. Ranganathan, extension of operation of space vector based low switching frequency PWM strategies using different over-modulation algorithms. IEEE transactions on power electronics, volume 17, issue 5, page 788 to 798, September 2002. You can download these, if possible, you can download these references, and you can go through these research papers, and you can find more vital information about over-modulation in PWM voltage source inverters using sine triangle PWM and using conventional space vector based PWM techniques. With this, I will end my today's lecture. So last 3 lectures we have dedicated to over-modulation. We have studied from different perspectives. First, from sine triangle PWM perspective and then from conventional space vector based perspective, and we have seen the similarities between the two. For example, m equal to 1.33 is similar to m equal to 2. M equal to 1.33 is in conventional space vector PWM technique is similar to m equal to 2 in sine triangle PWM technique. Similarly, m equal to 2 is similar to m equal to 2 in conventional space vector PWM technique based overmodulation is similar to m equal to 3 in sine triangle PWM based overmodulation. Okay, so please go through these lectures, these 3 lectures, and in case of any queries, any doubts, please put your queries on the group. Okay, I wish all the best to all of you. Thank you.